Hello, thank you all for coming, and thank Google for having me. Today, we're going to talk about Swift for TensorFlow. At a high level, we're not going to do anything more technically complicated than run through an MNIST demo a few times. The purpose of this presentation is to try and help you understand what exactly is happening under the hood whenever we run our code. Swift for TensorFlow is composed of a few different pieces: the Swift programming language itself, LLVM compiler, neural networks, some auto differentiation, and then sort of the XLA TensorFlow library. My hope is you kind of understand these pieces and how they fit together. Along the way, we're going to do some demos of, our demos will run on various different hardware, so CPUs, GPUs, and then ultimately a TPU in the cloud. And then at the end, we'll do a quick recap, and I'll leave you with some next steps, where to go from here. At a high level, these are sort of the components that make up Swift for TensorFlow proper. A large portion of the project was sort of started as a branch of the Swift programming language. About half that code has been upstreamed into Swift proper, so it's part of the 5.3 release. You can download that part today. And the team is working on getting the rest merged eventually. We'll also use some pieces of the Swift package manager so we can sort of pull down some other code and useful tools from the internet. The LLVM compiler is a large piece of Swift's power, and so we'll look a little bit at that and how that works. And then the Swift APIs proper are kind of the core of Swift for TensorFlow. This is sort of a set of neural network operators, although perhaps more broadly, you might think of them as being able to do math in general. The big thing that Swift for TensorFlow gives you under the hood is this idea of automatic differentiation. This is a really powerful tool that allows us to simplify building complicated neural networks. And so we'll try to break down how exactly that works. And then we'll look a little bit at the accelerated linear algebra library, or XLA as it's called. This is part of the larger TensorFlow project. And so by using it, we can bridge into the larger TensorFlow world. And by extension, we can use this to run our code on new and exciting forms of hardware. Before we can talk about Swift, though, I think we kind of have to talk about, sort of the motivations for its existence. So at one point in time, all programming was done in assembly. Out of this sort of Cambrian era, we'll say, there were a number of interesting ideas that came out, but one of the big ones was the C programming language. This kind of let people code in a slightly higher level language, but then they could recompile their code to run on different platforms. This really, in turn, sort of begat the whole Unix explosion and many of the concepts that we consider to be sort of the primitives of computing today. There are a number of high-level languages that came out of this era. One of the interesting ones is a programming language called Smalltalk. In order to simplify building larger and larger programs, Smalltalk kind of popularized this idea of message passaging, sort of loosely decoupled actors, sort of with a shared protocol for talking together. So a company named Apple really liked this Smalltalk concept, and so they wanted to try and code with it more all the time. But in the process of trying to bring Smalltalk to run on their Macintosh computers, they discovered that there was kind of some limitations to how fast they can make things go and stuff like that. So they created a set of Smalltalk bindings for the C language called Objective-C, and this was the backbone of Macintosh and programming in general for many, many years. A common theme whenever we sort of look at this sort of history of programming languages is this sort of idea of speed versus safety. We have languages that can go basically as fast as possible, we'll say, but they have sharp edges. Things can break, programs can crash, and all sorts of interesting states can be achieved. We can sort of try to add sort of safety checks, layers of abstraction in order to make it easier to build and reason about our code. But oftentimes, these sort of tools have a cost. So on personal computers, oftentimes, we can just build bigger and faster machines, and we don't have to think as much about this. But incredibly in the real world, embedded in sort of edge devices, this sort of usage of resources is a really, really big deal. we might think of the difference between, say, 1 megabyte and 2 megabytes of RAM as not being really that big of a difference. But for a product that's going to be shipped out to, say, millions of things that need to run on their own for years on end, this can be the difference between profitability or not. And so as a result, whenever you sort of start shipping projects to the real world, you oftentimes have to become extremely concerned with conserving this sort of space and resources and stuff like that. So I think really the big driver of Swift was simply Apple bringing the iPhone to market. The phone is basically the ultimate embedded device. It's basically a computer that fits in your pocket. But in order to do this, to say run firmware updates in the field, to sort of work on networks where things don't always work perfectly, all of a sudden these sort of limitations really become a big deal. So as a result, I think there was a strong internal interest at Apple at finding something better than Objective-C to work with going forward. And as a result, I think that was a big part of the push for why they introduced the Swift programming language in 2014. Swift is actually, in many ways, a fairly pragmatic language. It's sort of designed to work with existing C and Objective-C code bases side by side. So this is kind of nice because we don't literally throw away, say, the 50 years of work that's gotten us here. Swift, after about a year, Apple converted Swift into an open source project. And so in 2015, they published it on the internet. There was a lot of stuff that happened in the first couple of years out of there, but we'll say kind of out of the chaos, an order emerged. And now there's like a strong and steady cadence of new releases, new features, and RFPs in order to sort of improve things. You might think of Swift as being only iOS or perhaps just a Mac programming language, but you can actually run it on Linux as well. A number of our demos today are going to be on Linux. And then as of the recent 5.3 Swift release, Windows has its own port. So basically, any sort of programmer around the world can be brought into the fold. But the big key concept really that Swift, I think, brings is sort of functional programming to this whole ecosystem. But it does so, I think, in a fairly pragmatic way. It doesn't really force you to really go all in on functional programming as some other tools like perhaps Haskell might do. And so as a result, we have type safety, which is an incredibly powerful concept which we can use to build neural networks, as we'll see shortly. LLVM compiler is what actually Swift uses under the hood in order to generate its code. The LLVM compiler is actually it's really cool how this whole ecosystem has blown up around this. And so we have all these other programming languages that are using LLVM as well. As a result, there's all these sort of different groups with different sort of ideas and programming styles that are sort of pushing the forefront of what is possible. TensorFlow, we'll look at it down here. We might think of TensorFlow as being a neural network library, but in reality, if you kind of get deep into it, it's basically a domain-specific language for generating TensorFlow graphs, we'll say. And so by extension, it can go directly into LLVM because it's basically its own programming language as well. This top part of the slide is a slide I stole from a Chris Latner's presentation from a couple of years ago. The big recent update, the latest version of LLVM, is now Fortran has become part of this community. And so going forward, the arcane powers of the Fortran wizards will perhaps become a part of this whole ecosystem as well. So let's look at some actual Swift code. What we have right here is literally going to be the first two lines of our demo. Import TensorFlow and import data sets. We get the import TensorFlow from our Swift for TensorFlow toolchain itself. So we get this one for free. But this second trick is actually a really important one. And so we get it by way of the Swift package manager. This call up here gives us a bunch of code on the internet. And so on the very first line, our code is going to reach out on the internet and be able to download the MNIST data set for us without really, and give us a nice little data set handler in order to build our models on top of. So what we're looking at here is the MNIST data set. It's simply a collection of hand-numbered 0 through digits, so 0 through 9. And then the purpose of our network that we're going to build is simply to categorize. We're going to look at this and say, is this a 0? Is this a 1? Is this a 2? Etc., etc. So towards that end, the very simple, basic first type of neural network we're going to build is called a multi-layer perceptron. This slide right here is showing us how the math for MLP actually works. And it looks a little bit scary at first, I'll admit. But I think the key concept to look at whenever you're seeing this here is all these arrows are pointing in one direction. What that means is that this network is directional. So basically, as a result, we can have sort of a deterministic pattern if we feed data into it. So right here, this is going to be our input nodes. This will be our first actual neural network layer. These are the weights and biases that feed into this neural network node. And then the second one has a similar set down here as well. This H piece is going to be the activation function. And then we have a second layer of neural network nodes with associated weights and biases as well in order to produce our loss function over here. Don't worry if you don't get all this at first, because we'll look at it more here in a bit. So this is what a very simple multi-layer perceptron would look like in the Swift for TensorFlow programming language. We have this flattened layer right here, and then 2 layers of densely connected layers, and then our final output layer. Our flatten operation is kind of a tricky one to wrap our head around, but I think this slide here at the bottom does a good job of doing so. We have what right here might look like a number 1 and a simple 1x4 matrix, 4x4 matrix. So what we're literally going to do is unroll it. So we just take one row at a time and sort of make a long string of numbers. The MNIST data set itself is composed of 28 by 28 black and white pixel sets. And so by extension, the 28 by 28 is going to produce an input layer of 784 neurons. Then for our 2 middle layers, we're going to use 512 neurons apiece. And then finally, our output layer is going to be composed of 10 neurons. So this right here is the code that does that. We go from 784 to 512, 512 to 512 again, and then finally 512 to our output of 10 categories to represent our 10 digits. The second layer right here is our forward function. This is where we're going to actually differentiate our neural network. But conceptually, we simply take an input, whatever was given to this network, and we sequence it through our flatten operation, our 2 neural network layers, and then finally our output layer, and then we return that. So this is actually a very large piece of the Swift for TensorFlow, how it works under the hood. And so I think it bears attention, it's important to look at it a little bit deeper. The multi-layer perceptron has this layer property, and this is in turn requiring us to implement this forward function as a part of a protocol. So let's look at that right now. Here's the actual layer protocol definition from the Swift API's codebase. There's a few different ways of thinking about protocols, but I like to think of them as sort of being type safety for functions. We require functions to talk together in a certain way, and by extension, the compiler can sort of look at your code and guarantee that it will work a certain way. Here's the actual call as function call, which just wraps our input to an output. And then this forward is sort of a piece of semantic sugar that does the same thing, but that was recently added. I simply like it because it's sort of more in tune with how a number of other neural network projects work. So let's do a very simple demo of running our one-dimensional MNIST multi-layer perceptron on the MNIST data set. Most people have not seen this, but Swift for TensorFlow has tool chains that you can download. And so you can download them and simply run them in Xcode directly. So let's look at what that would look at right now. Here's our very simple network. We have our two inputs and outputs. Here's the same code we were looking at before, and we'll look at all of the rest of this here in a second. But at a high level, it's a project. We can hit the play button, and after a few seconds, we're going to actually start training our MNIST network right here on my laptop. Okay, so our very simple network that we're training is now getting like 94% accuracy, and it's simply running locally here on my computer. Next, I think we should introduce the concept of convolutions. This is kind of a tricky concept to explain, but I think this slide is as good of a way of doing so as I have found. Conceptually, we're going to take an input picture, this background thing, and we're going to map it to an output picture. In the process, we're going to go through this small little 3x3 convolution, or kernel, as it's sometimes called. This convolution that we're looking at right here is all ones, and so it produces what's called an additive blur. I think this is about as simple of a convolution as you can find in practice. What it means is that literally our result over here, this 7, is going to be the sum of these numbers. 1 plus 2 plus 1 plus 1 plus 2 produces this output. So we calculate this number, then we move our convolutional window over a row, and we grab our next set of 9 pixels, and we repeat the process for the next output pixel. We continue this across the image, and then we go down a row and repeat this process over and over again until at the end we've mapped everything from the initial picture to the output picture. These ones, you can do all sorts of interesting games with these convolutional kernels, and this is a whole deep area of theory, but for our purposes, this layer is part of what the neural network is going to actually learn for us. And so that is the sort of one of the key tricks that the neural network is going to do. Max pool is a simple operator. I think you can wrap your head around it. The problem with this sort of additive, 3x3 convolutional step is it often produces a lot of data. So this max pool is a simple way to sort of reduce the amount of data we're working with. So we literally take each group of 4 pixels, grab the largest one, and map it to the next layer. Then as a result, we can take a group of 16 pixels and reduce it down to 4, and by extension, destructively reduce our data. So let's look at what a convolutional neural network would look like using these same concepts in Swift for TensorFlow. Conceptually, though, it's not really that much more tricky than the stuff we've looking at before. We simply add a convolutional 2D operator. This is given to us by the Swift APIs library. And we have 2 3x3 operators which sort of slowly increase the filter depth. Then we have our max pool, and then we can just repeat our sort of set of network layers from before. So in order to implement this, we simply then have to add one more layer to our forward function. So we take our input, we sequence it through 1 convolution, 2 convolutions, and our max pool. Then we take this convolutional layer and sequence it through our original set of nodes. So conceptually now, we're taking our input in this picture, 28 by 28 pixels, running it through a layer of convolutions. Then we sort of map down to the same 512 by 512 hidden layers, and then finally our output of 10 nodes. So now, let's spend a little time looking at the actual training process. The key idea is we're going to use a probabilistic technique called stochastic gradient descent in order to train our model. So this is simply showing sort of how we would set up the outside of our loop before we do so. We sort of create our model, we create an optimizer, stochastic gradient descent with a 0.1 learning rate, and then we get our data set from the Swift models dataset handler. Then literally, we're just going to go through our data 12 times. That's what this epoch count does. And then each time, we're just going to update our model internally each time in the loop. I found this picture on the internet, and I really like it because I think it really illustrates the concept of how we start with a randomly initialized network. We sort of run through a loss update step. We repeat this process over and over again. And then finally, at the end, we run it on some test data in order to produce our output accuracy and whatnot. So let's look at the actual gradient update step. I think this is the most important set of code in this presentation. And by extension, I think this is the key one, where most of the magic is happening. Our first line is just sort of a hint to the global sort of context or state that we're needing to do things in the training mode. But then literally, we're just stepping through each batch of data in our whole set of data. We grab for each batch of data, we grab out the raw data itself, as well as the labels. This gives us images and labels. Then we literally send to our model, and we have our model run on those images to produce what it thinks the predictions are for those images. And then we run this loss function called softmax cross entropy. This is a nice, reasonably easy to evaluate loss function that produces good results. So we literally compare what the model gave us with what we know the answers should be. Out of all this, we are produced with a gradient, sort of a difference between where we are and where we think we need to be. So then we simply take our gradients and we run our optimizer. It updates the model in the direction that it thinks the gradients actually need to be. To me, as a Swift programmer, the one piece of little line of code that pops out to me is this little ampersand right here. This makes this whole model into what's called an in-out variable, and by extension, makes it so that other things down the chain can modify things as needed. This is for the validation step. This slide looks a little bit scary, but I don't really think, if you stare at it, I don't really think it should be. Basically, once again, we provide a global hint telling the Swift for TensorFlow backend that we're just needing to inference now. We're not needing to update things. This is just some variables that we create. And then like last time, we step through our data set, but this time our testing data set, and we do the same sort of thing. We get the images and labels, we compare them to the model, and then for this set, we're just simply sort of adding the difference, the test sum, or the accuracy loss right here. And then likewise, we get the number of correct predictions, and then we add that to our list. So how many answers we got right, how many questions, how many times we queried the model in total. And so then at the end, we can simply output accuracy, which is just literally number of correct answers divided by number of total times the thing was allowed to guess. And then all this down here simply just prints out some of these training statistics for us to see in the command line. So let's do a demo of running our two-dimensional convolutional neural network on the MNIST dataset in the cloud. For this, we'll use the Google Colab. Many of you may think that Colab only runs Python, but actually you can run different runtimes. And so the Swift for TensorFlow team has worked with Colab in order to make it that you can run Swift code on Google Colab. And by extension, you can get access to GPUs and even TPUs for free. So here we are in Google Colab. If you look here, you can see we have all this going. This first line, is a really important one because this sort of goes out and fetches our data set and whatnot off the internet so that then we can run things. The only problem for our demo's purposes is that it takes a couple minutes. So, just be aware that this works, but it takes a minute or so to get going. I'm going to cheat and use a different notebook that I have here that I ran this command on already 10 minutes ago. So we can see that we have a live console right here, and that I'm programming things directly. So here's our code that we were just looking at, but now we'll just run our whole thing as a large call to Google Colab. We'll give it a few seconds to get running here, but then we'll be running our MNIST demo using a 2D convolutional neural network on a GPU in the cloud. All right, as we can see, our Colab instance has reached out to the internet. It's downloaded the MNIST data for us, and now it's actually training our simple neural network, but in the cloud using a GPU. I think this is a really cool trick to know because it enables you to play with a lot of this code for free. So next, I thought it would be good to take a little bit of time at looking at how AutoDiff actually works under the hood, because this is an important part of how the whole Swift for TensorFlow system works. AutoDiff is from the 1970s or so. It's not as new as you may think, but the recent history of adding it to the full-blown compiler and whatnot is kind of a really interesting way of extending its abilities to make it more powerful. At a high level, we might think that we're starting with a simple basic function, and if we know the derivatives, we can sort of calculate that, and by extension, the derivatives for the second step. AutoDiff sort of takes a different path, and it just sort of mechanically calculates these variables. The problem with symbolic approaches is that for neural networks in particular, they don't scale particularly well. What we're looking at right here is sort of what the derivative for a soft ReLU, which is a slightly different type of activation function, would look like in practice. So what we see here. But then if we apply a ReLU to a ReLU, which is a really common pattern you'll see, all of a sudden our second level of derivatives start to look a little bit scary. The thing is, we don't actually have to have perfect derivatives. If you remember a couple of slides back, we're using stochastic gradient descent, and so by extension, we're already letting a little bit of uncertainty into our equations. The flip side of this, though, is that if we're allowing a little bit of uncertainty in there, then we can also, instead of using absolutely correct methods, we can use approximately correct methods. So the way AutoDiff is often described to people is as the chain rule. We have sort of, say, this concept of our input data. We have, say, a layer of convolutions, another layer of neural network nodes, another layer of neural network nodes, and then our output. Then conceptually, in order to calculate this number here, we start over here, and we sort of calculate the derivative here with respect to this. Then we can go here and crack the derivative here with respect to C, and then we can go back to A, crack the derivative here with respect to B, and then finally get the answer that we're looking for. I think if your mental model of AutoDiff is the chain rule, on a certain level, I think that's technically accurate, but I think you're sort of missing out on some of the magic that's going on under the hood. The way AutoDiff actually works is that we construct a second graph and then use our first graph as inputs to the second graph. Then, by extension, we can solve for this second graph to calculate this end node over here. But the joy of this approach is that once we've calculated this, we can balance across these flows here. And so by extension, we get the original answer that we were looking for. What's cool about this then is that the compiler can, under the hood, literally introduce this whole second graph for us behind the scenes, we'll say. And as a result, we can get the answer we're looking for, but we have this whole second layer of stuff going on in order to significantly speed up and simplify our computations. The second level of this then is as long as all these nodes follow these inflow and outflow rules, then we can simply extend this approach by adding more and more layers. So the set of rules for implementing one of these nodes are what are called the vector Jacobian products. Basically, we can convert this backprop equation into sort of this mathematical formula that then, if we can guarantee that our nodes follow this rule, we can add them into this, we can auto-differentiate through them. So here's showing what the actual vector Jacobian looks like. It's conceptually very similar to the multi-layer perceptron we looked at before. We literally have an input, a set of weights and biases, an activation of sorts, and then our final loss output function. The second level of this is that we can sort of keep all these memories, all these variables in memory, and we don't actually have to calculate these Jacobian forms. So as a result, this makes it very easy to make sparse forms of our matrices, and by extension, this allows us to build larger and larger networks. So let's look at what an implementation of a vector Jacobian product would look like in the Swift programming language. Swish is another activation function that has recently become increasingly popular for doing neural networks and deep learning. The ReLU that we were looking at before sort of comes in here as a black line, 0 to this spot right here, and then it sort of shoots off at a 45-degree angle. What the producers of this paper found is that ReLUs, as a result, sort of have a tendency to get over-indexed on 0, we'll say. They have a tendency to sort of try and minimize things, and so they end up down in here. As a result, this kind of limits how far you can push ReLUs in practice. So Swish introduces sort of this little bit of penalty area right here when the function is near 0, and as a result, the neural networks end up sort of moving a little bit away from 0, sort of not trying to over-index on things. As a result, this kind of makes the gradients smoother, and so by extension, we can train larger and better networks by simply tweaking this little piece of math. This technique was popularized with the EfficientNet paper from last year, but we're also seeing it increasingly in reinforcement learning, where bumpy derivatives are a really common problem. So right here, what we're looking at is how a simple implementation of the swish function would look like. Literally x times the sigmoid of x. On a certain level, we can actually have the computer work with this, and this will work reasonably well. It can differentiate it. You know, we simply have two variables, and the compiler can figure out the rest for us there. The problem with this approach is that we're basically making two copies. You know, we're taking input of one x, and we're outputting two x's as a result. The problem with this approach then in practice is that every time we call this swish function, we're going to end up doubling the memory requirements of our equation. So this is, now we're looking at how swish is actually implemented under the hood in the Swift APIs. One of the joys of understanding all this math behind things is that while you know, maybe we can hope for the computer to make things simpler for us, but on the flip side, if we understand the math, we can hop in and make things simpler for the computer whenever it sort of starts getting introducing the joy of this is that we can hop in and make things easier for the computer because we know what's actually going to happen. So what we're literally doing right here is computing the gradient for the swish function manually by hand. That's what this line is doing. And so then right here, we're just simply returning our custom gradient for the swish function. The joy of this then, though, is we get rid of that previous step. And so now this keeps our memory usage down. And so this swish function can be used in practice. All these sort of like little tweaks and stuff may seem academic, but they're increasingly important in order to build larger and larger neural networks. What we're looking at here is a TPU v3 with approximately 2,048 nodes running in parallel. The Google team has been an important driver in sort of this whole area of building larger and larger networks and sort of exploring the limits of what is possible computationally. Broadly speaking, there's sort of this idea, we'll say, the scaling hypothesis, which says that the trick to building sort of advanced AI isn't really having sort of fancy algorithms or whatnot, but simply doing things, simple things, but at large scale. We might take a language model and give it, say, a megabyte or a gigabyte of data, and it might be able to output realistic looking data responses. But we can take that same model and say, give it a petabyte of data, and all of a sudden, many interesting full form responses will just start falling out of it. So this whole area of building things and trying to make them larger, in particular on TPUs, is an important, really important area of focus today. So how do you program TPUs? Well, a large part of it is a linear algebra library called XLA. TensorFlow proper supports XLA out of the box. But there's a handful of other interesting software. TensorFlow proper supports XLA out of the box. But like we saw with LLVM earlier, a number of interesting other ecosystems are sort of exploring ways to use these tools as well. JAX is a really interesting project. It sort of takes a simple NumPy style interface and allows people who have NumPy code to directly convert it into XLA code, and by extension, run it on these sort of large clusters. Since it's almost a minimal implementation, this result is extremely performant and is a really interesting tool to be aware of if you use NumPy. The Julia project, those people out there are sort of working with implementing XLA in their machining workflows. I've not followed their research closely, but I know better than to underestimate Lisp people. As of PyTorch 1.6, the most recent release, the PyTorch XLA libraries have reached general availability. And so if you're coming from the PyTorch world, you can have access to these compute clusters on demand as needed as well. And then finally, last but certainly not least, Swift for TensorFlow, by virtue of sort of using these compiler techniques, can also use these XLA libraries, as we'll see here in a second. What we're looking at here on the right is simply a graph from the recent MLPerf 0.7 results from a couple of months ago. They're showing that Google has a TPU v4 waiting in the wings, and soon we'll be able to train networks at least 2.x plus faster coming soon. So here are the modifications needed to run our simple MNIST network on a TPU using the XLA libraries. At the top is really probably the key trick. We sort of get, we'll say, a handle to a remote device running in the cloud. Then we literally take our model and we move it to our device. We get our optimizer, we move it to the device. Our training loop is more or less identical, but now we have to take our data and move it to our device in the cloud as well. But then there, we can literally run our model on our device data with our optimizer, and we can update it there in the direction of our gradients. So all the rest of our logic actually remains exactly the same. This last little line is the only little piece of XLA specific stuff here. This simply puts a large hint to the XLA compiler that it needs to stop listening for new instructions and execute this loop. So now let's demonstrate running a 2D convolutional neural network on the MNIST dataset using XLA and a TPU in the cloud. This first line is quite simple. This is how I created my TPU before the presentation. So I have it running and standing by. These are some shell variables you need so that the Swift for TensorFlow your Swift for TensorFlow code knows what TPU it's talking to. But other than that, everything else is roughly the same. So here we are running our MNIST data set against the TPU in the cloud. We'll give it a couple seconds to get going. It usually takes a few seconds to wake up. It's kind of difficult to actually observe a TPU at work, but what we can look at right here is the talk of traffic over our network interface. So what you're seeing right here is sort of our little virtual machine streaming information to the TPU and then getting responses back. This is how this actually works under the hood. So to recap, we built and trained a simple convolutional neural network. We talked a little bit about how Swift, LLVM, neural networks worked in general, and how AutoDiff can be combined with XLA in order to run our code on arbitrary hardware. And so we ran our demo locally in the cloud using a CPU, a GPU, and then a TPU on demand. So that's most of what I have for content. If you're interested in playing around with this Swift code, I would highly suggest you check out the Swift models repository and Google Colab. You can get things running in a web browser pretty easily. I've written a book. It will be out shortly called Convolutional Neural Networks with Swift for TensorFlow, so you might check that out. At 9 a.m. Pacific on Fridays, the Swift SIG group does video calls, so meetings. If you're interested, I would highly suggest you listen in. They usually have really interesting talks. In particular, I would like to say thank you to Ava for listening to a prior version of this presentation and giving me a bunch of feedback on how to improve it. If you're interested in AutoDiff, a number of today's slides were stolen from a set of lectures by Roger Gross, so a gentleman up in Toronto. So you might go look at him and his work. And then perhaps more broadly in Swift for TensorFlow, but if you're interested in learning how TPUs really work, sort of say the nitty gritty, I think the best way to do so is to go through the cloud TPU tutorials. I've learned a lot, I've done most of them at this point in time, and I've learned a lot in the process of doing so. And so I think that's a really good way to get started with TPUs in particular, and then perhaps deep learning in general. And then finally, you might say, I can't afford to run TPUs all the time. And towards that end, I would highly suggest you reach out to the TensorFlow Research Cloud. They provide credits. I found that they're quite reasonable in providing credits for you. And so I'd like to say thank you to them for providing these TPUs that I used to run today's demos. And with that, I'll say thank you for your time.